Assalamualaikum warahmatullahi wabarakatuh. Good morning and good evening. My name is Kashful Azim bin Muhammad Azmi, student ID TG25026. Now, I am presenting about failure mode and effect analysis, also known as FMEA. For for this assignment, I have chosen a residential air conditioning system as my case study. Alright, so AC system and the function. What is an air conditioner? An air conditioner is a system or machine used to stabilize the temperature, humidity, and general quality of air within an enclosed space, such as home, office, or vehicle. Most commonly, it is used to cool and dehumidify buildings during hot weather. So the primary function of an air conditioner, the system regulates indoor temperature, humidity, and air quality via a vapor compression refrigeration cycle. It utilizes sensors to monitor environmental feedback. So we all we all have used an air conditioner, but how does it work exactly? So an air conditioner works by removing heat and moisture from the indoor air and transferring it outside, relying on closed loop of circulating fluid called refrigerant. This process follows a thermodynamic cycle known as the vapor compression refrigeration cycle. Next, here we have failure mode and effect analysis table, also known as FMEA table. In this table, we have type of component, type of potential failure mode of the component, the effect of failure, and here we have SOD and RPM. For this form, I will explain it later, but first we will look at the first three. So for the first component, we have temperature sensor, which is thermistor, and the potential failure mode of the component is calibration drift. The effect of failure is inaccurate temperature reading or energy waste. The second component, which is compressor, the potential failure mode of the component are motor winding burnout, and the effect of failure, complete loss of cooling. Next, we have condenser coil, the potential failure mode, clogged with debris, and the effect of failure are poor heat exchange and efficiency drop. And last but not least, we have refrigerant lines. The potential failure is gas leakage at joints. The effect of failure, gradual cooling loss, compressor, and compressor damage. Okay, so next, this is risk priority number, or so known as RPN. To know RPN, first we need to understand the severity S, occurrence O, and detection D. So what is this tree? So, severity, impact of the failure on the system and the issue, scale from 1 to 10. Next, occurrence, frequency or probability that the failure mode will occur. And detection, ease of identifying the failure before it result in critical event. So if we multiply all these three, we will have RPN. But first, what is the scale of these three? So we will look at it. The scale or rankings from 1 to 10, and from 1 for the severity ranking, rank 1, which is none, which means there's no hazard at all, there's no danger. But for rank 10, it is hazardous, and there is no warning of it. Next is occurrence ranking. Also rank from 1 to 10. From 1, which is remote, which means it is a rarely a problem. But for the rank 10, it is extremely high, which means it is common issues, common failures. And next we have detection ranking, also from rank 1 to 10. Rank 1 almost certain, which means the failure it is very easy to detect. And rank 10, absolute uncertainty, which means no chance that design quarter will detect cause mechanism and subsequent failure. Now we have understand all these three. We will look at the table again. So for the first component, temperature sensor, or also known as thermistor, the severity is 6, occurrence 5, detection 6. We multiply those three, and we will have RPN of 180. Next, compressor, severity 9, occurrence 2, detection 3. Multiply, we will have 54. Next, condenser coil, severity is 5, occurrence 8, detection 4, RPN of 160. And last but not least, refrigerant line, severity 8, occurrence 4, and detection 4. Multiply all of it, we will have RPN of 256. Next, from all of those RPN, we need to make risk priority number comparison. So we will take the most high risk at the top and to the lowest risk. From the higher risk, we have refrigerant leakage, RPN of 256. The second, temperature sensor drift, RPN of 180. Condenser clogging, RPN of 160. Compressor failure, RPN of 54. So we will see here the refrigerant leakage is the highest, and temperature sensor drift the second. So why are these two have very high RPN? So refrigerant leakage and temperature sensor drift are identified as the highest risk due to difficulty in early detection. So because of the detection are very high, it's become high RPN. It's become a high RPN. Next, risk analysis. So the critical failure of a refrigerant leakage, RPN of 256. This failure has a high severity as it can permanently damage the compressor. It is particularly risky because small leaks are difficult to detect without specialized sensor. The second one, sensor inaccuracy, RPN of 180. Despite moderate severity, sensor drift occurs frequently. It leads to user discomfort and significantly higher electricity consumption if not diagnosed early. So the recommended action are For the leak detection, install electronic leak detector or utilize pressure drop monitoring via smart sensor to lower detection rating. And next, preventive cleaning. Implement a quarterly maintenance schedule for condenser coil to lower occurrence. Sensor calibration. Perform annual testing of thermistor against reference probes to ensure setpoint accuracy. And lastly, safety cutoff. Integrate low pressure switches to protect compressor during gas loss. And lastly, for the conclusion, FMEA is a vital tool for ensuring the reliability of HVAC systems by prioritizing high RPN failure mode such as refrigerant leaks and sensor errors. Maintenance team can shift from reactive repair to proactive data-driven strategy. And that is all from me. And again, my name is Kashful Azim, bin Muhammad Azmi, and thank you very much.